All right, so we did three-phase Y-connected inverter. Let me go back to the previous page here. This one. All right, so here's the topology, right, for three-phase, 6 steps inverter. And last time we looked at this, and we can see that the load is Y connected. How do I know that? Because all the loads are tied into the same common node, right? And input is DC, output is AC, three-phase. You have 3 legs in the circuit, in the topology right there, right? One for A, one for B, and one for C, right? And then depending on how you depending on which switches are conducting at any given time, that would determine how the DC is connected to the three-phase AC. And that's what's creating the AC voltages, and that's what's clever about this. And the lab this week, you're going to be building this circuit. Some of you have done this already on Tuesday. The rest of you will be doing it today. And here's the key right here, right? In order for this circuit to work, the key is to be able to generate or produce switching signals with proper timing. Keep in mind that every switching signal, as I said last time, has 50% duty cycle, right? So 50% duty cycle, and then depending on how you time them, then you should be able to get different voltage levels on the output. Again, that's what's clever about this method. And also another thing is that as you are creating these signals, notice that, as I mentioned last time, that 3 of the switches will be conducting at the same time, okay? So that's what you'll be doing for the rest of you today for the lab as well. And these are the 6 different states of the output, right? And each different state will have 3 different sets of switches, which will give you different level of voltages for A, B, and C. And since this is a Y connection, you're going to have phase voltage, line to neutral voltage, and line to line voltage, right? So line to line voltage will be just the difference between the phases, right? So here's the voltage waveform for A phase, for B phase, and for C phase. And then once you know how to draw, for example, or sketch these waveforms, then getting or obtaining line voltage will be straightforward. You just do VA minus VB to give you VAB, right? And then VB minus VC to give you VBC, and so on and so forth. And you can see the shape is different, right? The shape of line-to-line voltages, they are not as good as the, right? You can visually see that, right? The phase voltage is more sine wave-like than the line voltage, okay? So therefore, total harmonic distortion, which we will talk about in the, not the following chapter, but the chapter that we'll discuss next. We look more into THD. So the THD of the line-to-line voltage is expected to be bigger than the THD of the phase voltages. In case you're wondering what THD is, THD stands for total harmonic distortion. It's just a way for us to quantify level of harmonics in the system, right? The bigger the THD, the bigger the harmonics level in the system, right? And we'll talk about it, you know, in the chapter that we'll start today. THD is kind of misleading though, so you got to be careful how to use THD. Anyhow, the load that we talked about on Tuesday, those are purely resistive load. Now, what if the load is inductive like this? Oops, sorry. What if the load is inductive instead of resistive? Then you can go ahead and go through this section. I'm not going to go through this section in details. But if you have inductive load, then voltage will not change. You'll see the same shape for the voltage. Both phase voltages and line voltages. What's going to change is the current, because now you have inductive effect, right? As you learned from 212 or 211 even, right? You have Eli the Iceman, right? You have inductor, then that means current lags the voltage, right? That's from Eli. If you have capacitor, then the Iceman, then current leads the voltage, right? So here you see that effect right there, right? That's the same voltage, right? The same waveform. Nothing has changed there. But if you look at the current, is actually better, right? Because of the inductive effect. As I said earlier, Eli the Iceman, you can see that for phase A, where is phase A? Yeah, right. Oh, I don't know if I can line them up, maybe. Yeah, you can see that if you look at this voltage right here, right, that's ahead of this current. See, this current now is kind of lagging, right? So it's instead of a jump in the current, now the current is slowly decaying, right? The voltage is already steps down to this level. The current is still slowly or gradually decaying, which is good, right? In this sense, it's actually better because you can see the quality of the current, the output current is actually more sine wave-like than the voltage. So that's what you get. That's what your that's the gain that you get from having inductive load, is that the benefit shows up in the current, not in the voltage. Voltage stays the same, but current now has better quality, right? Okay. Now, in the next discussion right here, which I'm not going to go in details, I'm actually I derived the equation for each of these segments, right? You can see those are just linear segment, right? For a given step, you're going to have a linear change in the current. So you can actually get the equation for this current. It's not going to be one equation, it's going to be 6, I believe, right? For 6 segments, since this is a 6-step inverter. So I'm going to skip that. This is just there for your reference. Where is it? Right here. So this is the derivation. Right? So you're not responsible for covering this for the final, okay? But this is there for your reference that you could actually derive the inductor, the output current equation, right, if you like, and it's not that bad actually, right? You're doing lots of substitution afterward, but at the end you have, if you follow this section right here, should be easy to follow as well mathematically. They're not that bad, as I said, lots of substitution, but at the end you have the equation for all 6 segments. And by right there, see, those are the examples, right? So 6 segments, 6 equation, right? For each of the segments, you get 1 equation. And once you know the equations, then you could determine the value, right? The instantaneous value of the current at any given time. And of course, this equation will change as you change the values of the resistor and inductor. That's why I have those equations in terms of the tau, where tau and see that R and also V, it will change based on the DC source as well. So if you have different R and L and V in the system, then you can plug in those values and you get different equations. But again, I'm not going to discuss this. I'm not going to go through this in detail, so don't worry about it for the final exam. You can skip this, but keep in mind that we have a section that shows you how to derive that equation, just in case in the future you are dealing with a 6-steps inverter and you would like to derive the current. That way you know instantaneous current, right? You know what to expect, you know what to look for when let's say you want to know certain power at certain time, right, in the output side of the inverter. All right. This one though, I want you to really know, especially for the final as well. This one shows you the equation for the total harmonic distortion, right? Fourier series for the three-phase square wave. Fourier series for the output voltage has a fundamental frequency equal to the switching frequency, right? In our three-phase step inverter, the switching frequency is always 60 hertz. It's always the same as the output frequency, right? So in the US, that's going to be 60 hertz, right? In most Asian countries, that's going to be 50 hertz. Harmonic frequencies, right, noise out of outside of the, or also including the fundamental component for three-phase square wave, right? The one that we just discussed, they're predictable, right? The location of these harmonics are known, and that's equal to n equals to 6k plus minus 1, 4k equals to 1, 2, 3. So k is just constants from 1, 2, 3, and so on and so forth, right? So that's the locations of harmonic frequencies. So if let's say k is equal to 1, then the first harmonic frequencies of the voltage, for example, that's going to be what? 6 times 1 minus 1. So that's the first one, right? With the minus sign. So that's 5. Right? So this is beyond the fundamental component, right? This equation. The fundamental component, of course, is 60 hertz. So then 6 times 1 is equal to 6 minus 1, that's 5. So 5 times 60. So the next harmonic locations after 60 hertz is, what did I say? 5 times 60, so 300 hertz. Okay, so if I were to draw the location of the harmonics, right? The very first one, of course, is the fundamental component, right? And then the second one is 5 times. What's the third one? Well, third one is when you apply the plus sign. So that's 6 times 1, that's 6, plus 1 is 7. So 7 times 60, that's 420, right? So it's going to be 7 times the fundamental component, and so on and so forth, right? So it's nice to have this equation because now we can predict where harmonics will be located if you have this inverter. Once you know how to predict the location of harmonics beyond the fundamental component, then you can start designing the proper filtering, right, for this. So you need to get rid of these harmonics by having a low pass filter. All right. And so these following equations, since we are dealing with Y connection, as you know, Y connection, if I just draw using 3 single phase winding, right? A Y connection is the one that has common point, right? Such as this one. So this goes to A phase, right? This goes to phase B, and this goes to phase C. And here's the common point right there, right? Let's call it neutral. And you can see that we have 2 different voltages. We have phase to neutral, right? And then we have line to line, or phase to phase. Okay, so for phase voltages, there's the equation to describe the harmonic content, including fundamental component. That's for phase voltage, for phase voltages, right? I use LN, line to neutral, and this one is for line to line, line voltage. Okay, that's why I use the subscript LL, right? So if you are asked to determine the 5th harmonics of the line to neutral voltage of the output voltage waveform of this inverter, then you can just apply this equation and plug in n equals to 5, and so on and so forth. Are there any questions on this?
I had a question.
Go ahead.
That n equals 3, 9, and so forth is eliminated because of alpha, right? That firing angle?
That's different, okay? That's the previous inverter. The previous inverter is multi-level. This is a 6-step. So there is no alpha here, right?
Okay.
So if you look at the switching signals, these are all fixed. There is no alpha.
They're all like 50% duty cycle.
That's correct. Already. Exactly. Well, you probably remember already, right?
Yeah.
This one, right? So this is a different type of inverter. This is a 6-step, 3-phase inverter. What you're referring to as alpha is the multi-phase.
Yeah.
I keep saying multi-phase, multi-level.
Single phase.
Yeah, multi-level. It could be single phase, it could be 3-phase, right?
Yeah.
Yeah, but that's multi-level.
So why are the multiples of 3 left out then? Like what's causing that? What's sort of picking those out?
Oh, just the way it the symmetrical property of the waveform, right? You have to go back to Fourier series, 228, isn't it? 228. There's certain properties of the waveform where the odd numbers disappear, where some triplet harmonics disappear. So unfortunately, I don't remember the unique properties. But yeah, that has to do with the unique properties of the waveforms. Symmetrical property of the waveforms.
Okay, it's just as you add them together, even though each step may have that 3, as they add together, they kind of get eliminated.
I think so. So. Yeah.
Thank you.
Okay. All right. I can just skip this one because this is inductive. That's inductive load, so I'm not gonna go deep. Oh, okay. So here's an example of simulation of 3-phase inverter with Y-connected load, right? It's purely resistive, and that's how we time the signals, right? And on the output, as expected, we know that's going to be line-to-line voltage, right? Because of the shape. I know this is line voltages, and look at the harmonics content, the harmonic content. Now we know this is number 1, this is number 5, that's number 7, right? As we discussed earlier, right? And what is this one? 6 times 2. So that's 11 and 13, 11 and 13, and so on and so forth. Okay, and then here's the phase voltages, right? Better shape than the line voltages. It's more sine wave like shape. And the same thing, like you can see the same harmonic level, not harmonic level, sorry, harmonic locations. But the level, if you look at the levels, this is smaller. Right? It looks like it's smaller than, relatively speaking, with the fundamental, right? If you compare, if you normalize, I should say, if you normalize all of these harmonics with respect to the fundamental component, the line-to-line voltages, I should say, would have a bigger harmonic levels than the phase voltages, and that should make sense, right? Because of the shape. Phase voltages, the shape is more sine wave-like, therefore harmonic level should be less than the line voltages. Okay, locations are the same, 5, 7, 11, 13, and so on and so forth. Okay, and if you don't like this, if this is too noisy for the output, if the output is very sensitive to harmonics, to harmonic noise, then you definitely need to include filter. And I attempted to do that with this LCL filter. So I'm inserting filter in between the inverter and the load, right? So by doing that, look at what happens. Beautiful, isn't it? You got beautiful sine waves from square wave, almost like a magic. This is why I like power electronics so much, right? Because you are shaping the DC into AC, and the AC looks ugly, but then we apply different E concepts to, in this case, filter, right? Filtering concept from circuits to get a much better output voltage. Beautiful sine waves, as you can see, right? And if you take FFT of that, right, this is time domain, of course, and this is frequency domain. You can see by having those that filter, I'm able to eliminate all the harmonics, right? The harmonics disappear, right? Okay. Same thing with the phase voltages. Oh, sorry, right there. What happens? Right there. Are there any questions on this? Notice that I'm using LCL. I try to use LC, and it's really tough because any reasons why it is tough to use a second order filter for this one? Anybody? Why is it difficult to use just LC? I have to use LCL.
You want a steeper roll off so you don't take out that 60 hertz?
Absolutely, very good. That's what I meant earlier by applying, different concepts in EE. Everything, start to click when I took power electronics. Oh, that's why I learned about, higher order filters. Because this is where I could implement that, knowledge or a skill that I learned from previous classes, right? So it's not just learning the math for the sake of math. Now I'm able to select cutoff frequency, the right cutoff frequency, and the right roll off, right? And then design my filter that way, right? So that's what I like about engineering, to be able to apply math, not just use math, not just learning the math, but apply them, right? So that's a good example where you can apply math. All right. Okay. Delta connected is the same way. I'm not going to go through this in detail because it's the same exact, the same concept, right, as the Y connection, except now you look at load, right? These are all delta connected, right? The loads are all delta connected. And yes, the way I drew it is, it's clear that this is delta, right? But when I teach 212, for example, right, same as Y, right? In a lot of textbooks, they draw it this way, of course, right? So that it is clear that it is a Y connection, right? Like that. Okay. And delta, you can see the way I draw it looks exactly like delta. But in real world, do not expect to see the shape, right? I always stress that when I teach 212. Pen over here, right? If you go out to a substation, right, don't expect to see that engineers will install, delta connection that way, right? You can actually visually see a delta. You would never see a delta shape like that in the real world. You would never see a Y shape in the real world, right? What you see is three windings, right? And you have to be able to trace how the three windings are connected, right? And apply what you learn, right? Go back to the basic, right? A Y, as we learned earlier, right, has a common point. So if you trace the wiring between the three windings, if they are tied together to a one point, then right away you know that's a Y connection, right? And that's pretty easy to see actually, in the real three-phase connection. You can actually see, oh, I can see that there are 3 points from each single phase connected to the same point. That must be a Y. So don't look for the Y shape, okay? Right? How about delta? Same thing, go back to the basic, right? All the basic that you learn in 212 or 211, those are very important. That's why I like to teach 212. For delta, what you look for is a loop, like this, right? So if you trace the wires, right, for this three phase, and if they form a loop like that, then I know that it is a delta. Or if you could not see the loop, at least if you know that they are connected one after the other, which means series connection, right there, then you know that it is a delta. Okay, so never look for that shape. I look for how they're connected, of course. Okay, so that's just something I would like to emphasize every time I see Y or delta connection. So delta, they're in series. Y, it has common point. Okay, are there any questions? And the same kind of signals, right? These similar to what you had earlier, right? The same rules apply. 3 switches at any given time, 50% duty cycle. The switches on the same leg cannot be on at the same time, otherwise you're going to be shorting the input, right? So the same rules. The only difference is that the shape of the output voltage will be different, right? In delta, theoretically speaking, you only have line-to-line voltages, right? But sometimes people also try to get line to neutral, meaning from this to the ground, if this is the ground, right? Sometimes, but in many cases, we're only concerned we're only concerned with line to line, right there. There is no I shouldn't say there's no phase voltage. In delta, line to line is equal to phase voltage, right? Okay. Any questions on that? All right. So here is the shape of the output voltages line to line, VAB, VBC, VCA, right? Depending on the 3 switches that are conducting, then you will be able to determine the levels, right? And in order to do this, of course, you need to draw the circuit at each segment, just like what we did in a Y connection, right? For example, for segment from 0 degrees to 60 degrees, right? We have S1, S6, and S5. So 1, 6, and 5 are on. If that is the case, then how are the load connected to the DC source, right? And you have to redraw that, and if you do that, you get this picture right there, right? See that? That's the first segment. You can see clearly that AC is shorted, right? There's a short across, see that? So I know that VCA is going to be 0. See that? VCA is 0. And then VAB, see VAB right here? Just do KVL around this loop right there. You can see that VAB must equal to plus VDC. So VAB must be equal to plus VDC. You see that? Plus VDC, right? And then the last one is VBC. Let me erase this. So VBC is from here to here, right? So that's VBC. So you can see the plus of the VBC is connected to the minus of the input. The negative of VBC is connected to the plus of the input, so they're inverted, right? So therefore, I know that for this time segment, VBC is equal to minus V, right there, right? And so on and so forth. Are there any questions on this? No? And just like this looks like the line-to-line voltages, right, for the Y connection. And what I forgot to mention is that if you are asked to find RMS of this, can you find the RMS of this? Or how do you find RMS of this? The answer to that question is yes, you could. How do you find RMS of that voltage? For example, VAB.
Is it like you would a square wave?
You have to square it, and then what?
Sorry, I meant how you do it like with a square wave. Since you're going to square it, it's going to flip to the top. So it's just based on a duty cycle?
Yes, very good. Very good. So I was going to ask, can we do this plus V divided by √2?
No, you have to do square root duty cycle, right?
Yes, that's correct. Very good. You still remember. But my question is RMS the same as this? Plus V divided by √2?
No,
No. Why not?
it's not a sine wave.
It's not a sine wave. Is it the same as plus V?
No, because it's not DC.
Because there's some empty segments, right? There's some 0 segments, right? If the signal is not signal, but output voltage is a full a simple square wave like that, if this is plus V, then yes, the RMS of this is plus V. But now we have 0 segments, which means you're going to have duty cycle, right? Okay. And what is the equation for RMS? What is the general equation for RMS? For any given periodical waveform? Equals? Come on, EEs, you need to know this. I'm glad that you remember that this is going to be a function of duty cycle, meaning you're going to square it. That means the RMS of this is the same as the RMS of this, right? Of this waveform right here, right? Because you're going to square it anyways. So therefore, the RMS of this waveform is the same as the RMS from here to here. You agree? Yeah, I don't need to include the negative. But what this, which is equal to, I'm just going to write it. So the RMS is equal to peak, this is plus V, this is RMS, right? Is plus V square root of the duty cycle. And you can find the duty cycle from the angle, right? So that's the equation that you learned from EE411, and I'm really glad that you remember this, because that's pretty good, right? That you remember this. But where is this coming from? Where is this equation coming from? So don't forget the basic, right? If you are given a different waveform, what equation you have to apply?
The root mean squared.
Yes. How does it go?
I think you square the function, like you take f of x and you square it, and then you take the average by taking the integral of that squared function and then dividing by, 1 over the period, and then take the square root of the whole thing, right?
Yeah, exactly. Very good. So don't forget this, the way I remember this, I believe I mentioned this in E410, I mentioned it again. There's the reason why this is called root mean square, right? So root, square root, mean is the mean function, right? And then square it, right? So anytime you forget the equation, I mean, you can always go back to the book, right? But as an EE, you should have this in your head already, right? Root mean square, okay? All right, so 6 different states of the circuit, right? I will go through those different output voltages, and so you get those inverter output. Okay. Same thing with the inductive load. You're not responsible to look at the inductive load, but it's there for your reference. Okay. And here is the delta connection. And you can see that just like before, right? I have all of these switching signals, right, for the 6 switches, and because of that, I was able to get the square wave. Right? Those are line-to-line voltages, and FFT for the 3 phases, right? And I don't know if I apply filter. I did, and then I apply filter again, and because of that, I was able to get a pure, not a pure, but very smooth sine, very close to pure sine wave, right? Okay. Any questions on that? Oh, okay. No questions? All right. If not, then the next part is on inverters, 3-phase inverter, PWM inverters. All right. Now, if you look at the circuit, it has not changed, right? It's the same as before. You can see the configurations. This is for Y connection, right? Nothing has changed in the circuit, right? So what changes then if you want to convert it into PWM, right? So the circuit stays the same, but what changes is the way you control those signals, right? Instead of using 50% duty cycle, right? Now you can use different ways of turning on and off those signals, right? Using what we call PWM controls, And by doing so, you're going to get different shape of the output. Okay. And how do we do that? Well, you learn from EE411 that if you want to get PWM in the controller, so imagine I have a controller, right? Controller circuit, right? And this will provide the signal to all 6, right? To all 6 switches like that. And inside this controller, right, you will have 2 different control signals. One is triangular waveform, the other one is the reference, which is the sine wave, right? The sine wave reference inside that controller determine the frequency of the output. So if the reference signal right here, which has much smaller frequency than the triangular waveform, controls the frequency of the output. So if you want the output voltage of the PWM inverter to have 60 Hertz frequency, then the reference signal will also have to have 60 Hertz in frequency. So the 3 sine waves right there would have 60 Hertz. Right? If you do that, then you get 60 Hertz on the output. The triangular waveform is there for the switching, the high switching purpose, right? So that's why the triangular waveform is much higher switching, much higher frequency, I should say, much higher frequency than the sine wave, right? And the triangular waveform is the one that determines or defines the switching frequency of PWM. Okay, so 2 different signals, right? Triangular waveform that defines switching frequency. So if somebody says, okay, I have a PWM inverter that has switching frequency of 10 kilohertz. So that means inside the inverter, in the hardware portion of the controller, specifically in the controller of the inverter, the triangular waveform that they use, right, that they're implementing in that inverter is running at 10 kilohertz. Okay? So that defines, the triangular waveform defines the switching frequency. The sine wave, as I said earlier, that would define the frequency of the output. Right? Now, since we have 3 phase, therefore, we have 3 reference signals, right? One for phase A, the other one for phase B, and the last one for phase C. So we have these 2 signals, control signals. I already mentioned that, right? Switching frequency from the triangle and reference from the sine waves. So then how do we control the switches using these signals? By comparing the 2, right? By comparing the 2 signals. If you just focus on the first one right here, right? Yellow, so that first sine wave right there, then you're gonna compare the sine wave with the triangular waveform. Anytime the sine wave is higher than the triangular waveform, then we will turn on, for example, the top switch on A. Okay, I will turn on this right there. So anytime the sine wave is larger than the triangular waveform for reference signal A, then turn on this one and turn off the other one. They're always complementary, right? Okay, same thing with the other ones, right? If you look at the second sine waves, for example, this one right there, you apply the same rule. Anytime that sine wave is larger than the triangular waveform, turn on the top switch on phase B, right? And then turn off the bottom switch on phase B, and so on and so forth, right? So here's an example where for phase A, if you focus on the first sine wave only, right? So here's the point or the segment from this point right there to that point right there, right? That's when the sine wave is larger than the triangular waveform. You see that? So if I draw the, what happened to my pen? Oh, right here. If you compare the 2, then sine wave is larger than triangular waveform. Then if you draw the straight line down from the first intersection of the 2 to the second intersection of the 2, then during this segment, you will send the high pulse to the top switch, meaning turn on S1, right? S1 on, what is the other one? S1 on, S4 off. Right? Okay, and so on and so forth. And I think you can do the rest. Any questions on this?
So is this when the triangle goes above that yellow waveform?
No, I'm looking at this segment right there. When the sine wave is above the triangle. See, from here to
Oh,
here.
got it.
Yeah. Yeah, it's the opposite. Okay. Any other questions? All right. So that's what you do, and you have, of course, you have to implement this in the logic circuits, of course, right? In the controller. So you have to have comparators and then amplify the output, right? And then use a driver to amplify the power, so you can not amplify the power, provide the power for you to be able to turn on the MOSFETs, for example, right? And here's an example of using ideal components on how to implement these control signals, right? You can see I'm using comparator and then amplify the signal and then limit the signals to only 10 volts, right? And then send it into the ideal switches. Of course, in reality, in the real world, you have to have drivers to turn those switches on and off. And there's the output of the controllers, right? For different signals for A, B, and C. Okay. So you can see now we are dealing with high switching, a lot more switching than the previous method, right? A lot more switching. And here's an example of a sine wave PWM inverter, right? So I'm implementing those signals, controller signals, into the same topology, right? You can see that I'm not changing the circuit. This is the same as what we had earlier with 6 steps. Right now I'm just changing the way I'm controlling those switches using this logic circuit. And if we look at the output before the filter, looks ugly, right? Or really ugly, because you can see all the switching, right? All of the switching, a lot more switching. But at least it has positive cycle, negative cycle, right? So you can kind of see the sine wave quality of this output. Not good, right? Because all pulses. That's why this is why it's called pulse width modulation. Because if you zoom in, right, the pulse width are varying with time, right? You can see, hopefully you can see clear from here, or maybe I can zoom in. You see that? So toward the center, toward the zero crossing, as you are going from the zero crossing to the peak of the sine wave, you can see the duty cycle gets bigger. You see that duty cycle gets bigger, and then once the duty cycle gets biggest, right, at the peak of the sine wave, then it goes down again. You can see the duty cycle decreases again because now it goes into the next zero crossing. Right. So imagine if you average this, if you use low pass filter to average this, then you're going to get sine wave, right? Because duty cycles start from small and then bigger, the biggest, and then decreasing again, right? Okay, hopefully that makes sense. That's what goes behind those pulses. And look at the harmonics, right? Now, yes, the signal looks ugly, but if you look at FFT, the time domain waveform looks ugly, but if you look at the frequency domain of the signal, then you can see that it's actually better, right? Because that's the first harmonics, which is what you want, right? And then these are the harmonics beyond the fundamental component. Why is that good? Why is it better compared to the square wave or 6 steps? Anybody? Why is this better than the square wave?
Further out, so easier to filter out.
Yes, you can see the locations, right? Locations of the harmonics is away from 60 hertz, right? Further away. Instead of, remember before, 5 times, 7 times, 5 times 60 was 300, right? So 300 hertz for square wave. Take a look at what happens if you do PWM further out, right? It's like around, depending on the switching frequency, right? So that's actually the same as the switching frequency, sidebands. These are called sidebands noise. So it's around the switching frequency. And switching frequency in this case, I'm guessing is 2.5 maybe. Oh no, I don't remember what. Oh, we can check. What's the switching frequency here? Okay, 45 times 60. 45 times 60, whatever that is. So 45 times 60, that's a very high location, right? Compared to 60 hertz, right? So that's 45 times 60 right there, around 45 times 60. So that's easier to filter, right? Okay. All right. And there's the line to line, I believe. Yeah, this is line to line voltages. Again, looks ugly, but hopefully after you filter it, it looks better. One thing though, I actually did not optimize this filter like I did for square wave. That's why if you look at the waveform, you can still see the ripples. I could make it better, of course, by having a better cutoff frequency, but too lazy to do it when I did it. So that's good enough. So you can see now from those ugly pulses, turns into a sine wave, right? With some high frequency ripple riding on top of 60 hertz. Okay. Any questions on this?
I had a question.
Yeah.
Is the general advantage of this three-phase method versus the previous one that you get cleaner output because the frequency you're introducing is way further out? And then the disadvantages is the higher switching frequency, which causes increased switching losses. Is that kind of the trade-off?
Yes, that's the trade-off. The trade-off with that is that harmonics are further out, so it's easier for us to filter. Even though I didn't actually show that here, sorry, I didn't showcase it here. But keep in mind that harmonics way out compared to the 60 hertz. But disadvantage would be that you got more switching, right? More switching action, meaning you got more switching losses, right? Imagine every single one of these pulses that you see earlier, that you saw earlier right here. Where is it? Right there. Every single time you turn on from zero, you turn on the switch, or not the switch, but the output voltage from 0 to 160, back to 0, right? All of these are switching, right? Imagine the switching loss that you're going to get on the switch, right? As it's going through this transition, a lot more switching loss. Okay. So that's why, because of those many switching losses, switching actions, PWM inverter is not being used for utility scale applications. Right? They use medium. They're being used for medium level, such as solar panels, but beyond that, it's too much loss to use PWM. Too much switching loss. Okay. When you are operating PWM inverter, make sure that you follow this as well. Let me see. We stop at 1:30, right? I keep forgetting, right? So then, remember, we have two different signals. Triangular waveform, and what is the other one? Sine wave, right? Sine wave. So in order for us to be able to control the output voltage, we want to control the frequency of the output voltage, which we know is going to be the same as the sine wave frequency, right there, right? But in order for us to be able to control the RMS of the output, V out RMS, what we need to do here, we need to be careful. If you want to have a linear control on the output voltage RMS, then you have to operate the inverter in what we call linear modulation, right? So linear modulation is defined from what we call amplitude modulation, MA. Amplitude modulation is defined to be the ratio of the peak of the sine wave to the peak of the triangular wave, right? So if the peak of the sine wave is, let's say, A, and the peak of the triangular wave is B, then it's going to be A over B, right? So that would define amplitude modulation. If the ratio is less than equal to 1, then we are operating the inverter in linear modulation. And this is the desired operation, because if you do this, then the RMS of the output voltage, or actually the peak first, the peak of the output voltage will be a function of the amplitude modulation times the input voltage. Okay, so input voltage is fixed, so the one thing that you can adjust is amplitude modulation. So if you want to adjust the output voltage, peak of the output voltage, which of course will give you RMS, right? By dividing it by 2, because this is going to be a sine wave. Then you just need to adjust MA. You need to adjust how the sine wave peak is compared with the triangular wave peak value, right? So that's what you do, right? So again, if the ratio is less than 1, less than or equal to 1, then it's linear modulation. Then you get this equation, right? That's this right here. Sorry, let me scroll a little bit right there. So that's the linear region right there. Right? So you're operating the PWM in the linear region, then output is MA times BDC. If you increase the peak of the sine wave to be larger than triangular wave, let's say like that, so starting to be larger than the peak of the triangular wave, then you get into overmodulation, the knee region right here, where the output voltage is no longer a linear function of MA times BDC, no longer this, right? That's why it's going to be harder to control if you do this, right? So this is to be avoided. Even worse is when you even make this peak to be much larger, such as this, right? If you make the sine wave reference to be much larger than triangular waveform, then you're going to end up with a fancy square wave, right? Because half of the cycle, the sine wave is always larger than the triangular waveform. The other half of the cycle, the sine wave is less than the triangular waveform, right? So therefore, you're going to end up with a square wave, right? That's why it's called square wave region, where the amplitude of the output is fixed at 4 times VDC divided by pi. Okay. So yeah, make sure when you are operating PWM, you're operating it in linear range, linear modulation. Any question on this? Okay, I've already discussed that. All right. These are just a table to show the difference between the 6-step that we covered earlier and PWM. I'm comparing the equations for getting the RMS of the output, line-to-line value, quantity of the output voltage. For 6 steps is 0.811, for PWM is 0.731 MA times BDC, and so on and so forth. This is just a table to summarize the different equations that you'll get from 6 steps or from PWM. So you can compare the two, right? Given MA and VDC, which one is going to give you a better value, right? So you can get it from this. Notice that THD, the last row, for 6 steps is less than 29.66, and it's fixed. It's a fixed value. It doesn't matter what VDC you put in. Same thing with PWM. Right? It's a fixed value. Doesn't matter what MA, what VDC you are using, always going to end up with the same THD. Right? Those are normalized value. That's the reason why you end up with the same value for THD, because again, THD is a normalized function, right? So, but it's interesting to see that 6-step has less THD than PWM. And this is what I meant earlier by saying that THD could be misleading. That's why you need to be careful when looking at inverter through by just looking at the THD. It could mislead you, right? For example, here, this is a good example where it shows that THD of 6 steps is less than the THD of PWM, right? So if you have not taken this class before, right away you will say, oh, 6 step is going to give us, bad output voltage. Oh, sorry, not 6 step, PWM, because THD of PWM is bigger than THD of 6 steps. If you have not taken this class, then you probably think that, oh, THD of PWM is worse. Therefore, the AC that we get from PWM is bad, right? It's worse than 6 steps, which is not the case, as you already learned, right? We know that the THD not the THD, but harmonics of PWM is at much higher locations compared to the fundamental component. So therefore, it's better because it's easier for us to filter. Right? The reason why the PWM is bigger in terms of THD because we have more switching, right? In the topology, in the control, we have a lot more switching than 6 steps. That's why THD of a PWM is not much higher, but it's higher than 6 steps. This could be misleading then, right? So be careful. Not just look at the numbers. This is what I'm trying to get at. Not just look at don't just look at the number for THD, but also look at the location of harmonics, right? Location, 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 right? So take a look at the location of the harmonics, not just the THD number of the harmonic, right? The THD could be big, could be big like this one, but when you look at the location of the harmonics that produce that THD is actually better than the 6 steps. Why they are better? Again, because they are much higher than the fundamental frequency. Does that make sense? Yeah, go ahead.
Is all that THD when you filter it out lost energy?
When you filter out, it's not lost energy. It's actually you preventing. If you don't filter it, first of all, right? If you don't filter these THDs, then this THD energy will be absorbed by the load, right? Which are something that the load does not require. Basically extra energy, right? The load is absorbing extra energy. Not good, right? Efficiency-wise, you agree? Yes or no? First of all.
Sorry,
okay.
I was muted.
Okay, so by filtering it, you are blocking the frequencies, right? Harmonic frequency to be present at the load. So you're blocking these frequencies. So then these frequencies are not present at all in the load, and so the load now is only absorbing 60 hertz component, nothing else. So it's more efficient that way. Okay. Does that make sense?
I guess my misconception is if you have like say a 2-pole filter or something like that, or even a single pole filter, and you're grounding the higher frequencies, doesn't that represent lost energy?
You're grounding the what frequency?
Say whatever higher frequencies above 60 hertz.
Oh, you're grounding the higher frequencies. Yeah. Well, ideally filters are what? Reactive components, right? You learn from 212 that reactive components, ideally, they do not absorb power, right? P of L is equal to 0. P of C is equal to 0.
Yeah.
Yes. So if you have an LC filter like this, and basically you are providing a low impedance path for the high frequency to go to ground and the 60 hertz to go to the load, right? Ideally, it's not going to cost you any watts.
Just going to give it back, yeah.
Right? So, but ideally though, but at least theoretically, that's what we learned, right? And so therefore, in the process of blocking these frequencies, we're not going to lose any watts. But of course, in real world, we're going to lose some, but not big,
yeah,
right? We're going to lose some. Yeah, we're going to have ESR, we're going to have DC resistance of the inductor, right? But still, it's going to be a lot lower than passing, this energy into the load. Does that make sense?
Yeah, because the load is going to be more primarily resistive than whatever like LC network you have.
Oh
Yeah.
yeah.
Okay.
Yep.
That makes sense.
Okay.
Thank you. That's just something I've been wondering in general. So thank you for clearing that up.
Oh, you're welcome. All right. I think that's it for inverter. This next one, I'm not gonna ask you to review this for the final, but I think it's still good to know that there is another method of getting AC out, right? What we learned earlier from DC, of course. So another way of getting AC from DC. What we have earlier is that we have DC to AC using what is it again? Square wave and PWM. But now, what we have here, or maybe I should do it this way. A typical application of an inverter is this: your input is AC, right, from the utility, but the output is also AC. Input has a fixed frequency. Output, you want frequency to be adjustable, right, or fixed. It doesn't matter, right? But you want to do this the more efficient way, right? Not only frequency, but also amplitude. There you go. Okay. So how do you go from here to here, right? What we learned so far is that you have to do a rectifier first from EE411, and here we'll give you DC, right? Once you get DC, then you can implement what we just learned this week, right? Inverter. So you have rectifier and you have inverter, right? So now, then you can achieve the objective of having output from a fixed input, right? This should be V in, sorry, V in. Fixed frequency input, fixed amplitude of input to adjustable frequency out and adjustable RMS out, right? By introducing a rectifier followed by an inverter, right? So this is called a two-stage approach, right? Where you rectify first to DC and then you invert it back to AC. There is another method where we can directly convert AC, right? The same objective, AC to AC, right? The same objective, adjustable RMS, adjustable frequency. However, we can actually do a direct method, one stage. I keep putting F out, okay, like there, right? So one stage method. This is called cycloconverter. Right? So no two stages. This is just one stage, right? So how do we do this? By to me, it's very clever as well. I'm just gonna explain the concept behind this. But here's the circuit, right there. So you have three-phase input. There is no rectifier. You can see, right? And then the output is AC. So what you have in cycloconverter is that you have back-to-back bridge converters. Okay, back-to-back. The first one is for the positive current. The second one is for the negative current. Okay, so that's why you have back-to-back. Again, the left one is for positive current. The right one is for negative current, right? Because we want AC. Okay, and there are different constructions of this, different topology, not different topology, different configuration, I should say. This one is a cycloconverter that has inductors, right, in reactors in between. The reason being there's going to be a circulating current around this bridge, and we want to limit that because that represents loss. And to limit that, we use a reactor or inductor right there. Okay, and then in order to improve this, because this is going to be costly as well as lossy, we use what we call non-circulating cycloconverter, such as this one, right? And the difference between the two is this, besides the reactor, of course, is that in the first type, the circulating type, those thyristors that you see right, are always on, they are not always on, sorry. Those two converters, the P converter and the N converter, are always operated at the same time. Whereas with a non-circulating converter, if we have a positive half cycle, if you want to create a positive half cycle, then only turn on those switches, those thyristors that would correspond to the positive half cycle, right? So only turn on those for half of cycle. And then the other ones turn off for the negative half cycle. So not non-simultaneous operation, basically. Right? That's how we can prevent circulating current, right? Because we're only operating one converter at any given time. Okay, so that's the difference. But again, I'm not gonna ask you to cover this for the final, but I think it's important for you to at least understand the concept behind cycloconverter. It's clever. Okay? How? Like this. I'll show you. We learned from EE411 that if you have, if you have a three-phase bridge converter like this, right? You can convert AC to DC, right? Like that. A, B, C, right? And here's the output, right there, right? The output is going to be DC. Now, what we learned in E410 is that I can apply alpha, firing angle to these thyristors, right? And so the output is going to be a function of alpha. Agree? So the output is going to be like, you know, remember, oh, you know what? I think I still have it here. Yes, right there. Remember this waveform? You probably don't miss this waveform at all, right? Remember by applying alpha, you get this kind of waveform, right? Remember that for different alpha, right? Okay, so that happens if alpha is fixed, right? If alpha is fixed. If so V out as a function of alpha, this is DC, is equal to 3 VM line to line peak divided by pi, cosine of alpha, right? So I know that if you change alpha, then you change the DC, right? And typically for a rectifier, alpha is fixed. But what if I also change alpha with time, alpha t? Then I have V out of alpha t equals 3 VL line to line pi cosine of alpha t. Meaning, right, if I could somehow time the alpha such that the output, the average of the output voltage follows a sine wave, that'll be cool, right? So let's say for when it close to the zero crossing, we're going to introduce alpha to be equal to close to 90 degrees. That's going to give the average output voltage to be close to zero right here. And then as time progresses, right, I'm going to change alpha to something lower than 90 degrees, even lower. Then you get a slightly lower, I should say, slightly lower, and then you're going to increase the average voltage, right? And then slightly lower again, slightly lower again, slightly lower again, until cosine of alpha is equal to 1. Basically, alpha is equal to 0 degrees. Then you get the peak, the maximum average output voltage. So imagine if we can do this at any single, as time progresses, at different slices of time, right? So T1, T2, T3, and so on and so forth. You keep changing alpha. So then the average of the output voltage changes as well. The average of the output voltage changes as well following that alpha. You see that? Isn't that clever? Whoever found this is a genius, right? So you just, instead of fix alpha, let's change alpha with respect to time so that the output follows a sine wave, right? So that's the concept behind cycloconverter, right? By changing alpha with time. And so if you look at this one, I'm just going to go straight to the output. That's the way, that's a method to do to give you the alpha, to give you the varying alpha with time, right? This is showing you how to do it. Yeah, see, the alpha is a function of time. Anyhow, let's see, right there. Here's an example, right? So you have 60 hertz component, right? All of these are three-phase 60 hertz. The faster frequency, that's 60 hertz. The output, the lower frequency, you see that by changing alpha, you are changing the average output voltage. You're changing the output voltage waveform. You see that? Depending on alpha, right there. And then if you filter it, then you get this waveform right there. Okay, clever.
Professor,
Yeah, go ahead.
can you go from single phase to three phase with this by just paralleling 3 and altering the phase by changing alpha for each of the parts, each of the bridges, or?
I think so. I think so. Yeah. You just have to introduce, like a phase shifting transformer. That's one way to do it. Yeah,
Oh, I didn't know they had phase shifted transformers.
Yeah, they do. Yeah, you could do that. Absolutely. Yep. Also, you can time the control like you are suggesting. That could be done too. Right. Okay. Does that answer your question?
Yeah, it does.
Okay. So now again, this is a clever way of avoiding the use of a DC link, right? You don't need to do a rectifier first and then invert it. Now you can do a direct AC to AC converter using a cyclo. Now, what is the limitation, you think? Can you name a limitation? At least one? There's two, or there's more, maybe. What are
power quality?
Yes, power quality is bad, as you can see. What else?
The frequency of your output waveform can only be so close to the other waveform before it starts getting really choppy.
Very good. You can see that in order for this to give you a good quality of the AC output, the frequency of the output voltage is typically limited to 1/3 of the input voltage. Typically, is limited to 1/3 of the input voltage, right? So if the input voltage is 60 hertz, then the best output voltage you can get, or not the best, but in order for you to get a good quality of AC output, then the output has to be at the most 20 hertz if the input is 60. But if you want to get 60 hertz, then the input has to be 3 times 60, 180. But then how do you generate 180 hertz, right? So that's the problem with this, right? That's a big problem, is that to get a good quality of the output voltage, the frequency has to be at the most 1/3 of the input frequency. And since we know that in our system, right, AC system, 60 hertz is very common, is predominantly 60 hertz, then the best AC output voltage you can get at the most is 20 hertz. So it's 20 hertz or below. Beyond 20 hertz, it's going to get so ugly here, right? With all of these harmonics, right? That is the main reason why cycloconverter is rarely used. And they're being used mainly for very big drives, very big controller that controls speed of motor, huge, like tens of horsepower to hundreds of horsepower motor, maritime type of applications, right? Big machines, right? So it is still being used, but not to the extent like the other techniques, okay? The other technology. Any questions on this?